recording. And share the application. So I'm going to vote on behalf of the people who might have forgotten that it was at 3 today and go ahead and start, knowing that the recording will catch it for them. Because I think that the most valuable part of today is going to be in the practice that we get and the hands-on stuff rather than in some of this lecture stuff, and it'll be easier for them to teach themselves with the recording the stuff from the lecture versus actual doing stuff. Okay, so today we're going to go over the relational model and relational databases. Shurab and Mahanez could just as easily be up here teaching this class, and which is great because they're going to be a huge help when we do some hands-on work. And Jan, I'm really interested to know, after this class, how much of this you covered in your class over at UA Little Rock on databases versus how much was not in there. I'm hoping that it was all in there, but it'll give me kind of a good feeling for what that class covers and doesn't. So if you can just kind of let me know either way, that'd be awesome. So the learning objectives, I got those, I did get those posted. Is to basically understand what a relational database is and be able to describe it versus other semantically similar but not exact alternatives. This is a really important part, given a data collection form, and we're going to use these ones. If you have yours from last week, that's great. If you don't, come up and get another copy. Those there. Sorry for those of you online, I was handing out papers. And so you'll notice the papers are the same as last week. They're pretty much random clinical forms that we got from the web, nothing special. And the cool thing is that the relational database theory works for storing any kind of data. So this like random forms we found on the web, we're gonna look at how to structure that data in a relational database table. We're gonna go over at the end entity relation diagrams, and then we're gonna explain several ways to determine what data are in an information system. Often if you're using data for secondary use, or it wasn't you that built the database, one of the first stumbling blocks, aside from how do I get access to the daggone thing, is how do I know what data are in there and what data are not in there. So we're going to talk a little bit about that. We're going to talk a little bit about how data elements and control terminology work with relational databases. Hopefully that'll become obvious from some of the earlier exercises. And then last but definitely not least, we're going to execute simple SQL select statements on a relational database. And Shurab and Mahanez have something cool. They have found an open source relational database called Postgres and some free available data on the web. And they have a way, I think, so that people can download it and play with it on their machines in not too painful of a manner. So we're going to try that for actually executing some of the select statements against a real database, which is really cool. And so the topics that we're going to cover are really simple. We're going to talk a little bit about the relational model. I do have the slides in here about CODS 12 rules. I will post the original paper from CODS 12 rules back from the 1970s. COD is one of the people who conceptualized of using the relational model to store data. And he's sort of generally thought of as the founder of relational databases. So I'll post the original paper. It's more for your perusal. You won't be tested on some of the more detailed stuff in the paper. And I'm not going to test you guys on CODS 12 rules. They're nice to know. It's lovely to read. If your career is not in databases, it's really not that important. You just need to know that they exist and that CODS 12 rules are sort of what defines a relational database. Not that a lot of the products actually meet to a T every single one of CODS 12 rules, because they really all don't. So those are the topics that we're going to cover. So the reason why we're going over this is that a lot of data today are stored in relational databases. A growing number are stored in NoSQL or not really non-relational, but some people think of them that way, databases, so alternatives to relational databases. And as a researcher, as somebody who works with data, it's important to be able to understand how the data are stored and to understand the relationships between data in the database, so that you are more informed than Dilbert's boss about what a database is. So there are several different types of data storage. The first is a file-based system. This is sort of old-timey data storage. And in a file-based system, data are basically just in files. Like if you took an Excel spreadsheet and sent that to somebody, that's a file. Or if you saved your data in an Excel spreadsheet in CSV format or comma-separated variable, just sort of plain text format, and sent it, you would be sending them a file. And if you write a computer program in some language that uses data in some way, a lot of people store the data that the program uses or writes out in files that the program accesses, and those are file-based systems as well. A spreadsheet provides a little more structure in that there are rows and columns in a spreadsheet, although general spreadsheets really don't enforce any kind of rules. You're on your own to enforce some of the rules that we're going to talk about a little later today. And then there are things like pseudo-relational databases. So when Microsoft Access first came out, it wasn't a real relational database, but it could kind of look and smell like one. But if you executed very detailed queries on that database based on set theory that we'll talk a little bit about today, you might get different results than you would expect, because it wasn't a true relational database and didn't conform to all of those rules that we might expect from set theory. So there's a lot of pseudo-relational database products out there that sort of operate like relational database but aren't really. And then there's relational databases that sort of 10 years ago were the zenith of being able to store data. But as data have gotten more large, the engineering behind relational databases hasn't always kept up. And so there are definitely many approaches that one might take to structure data in a database that would render the performance really bad when you have a lot of data in there. In other words, somebody might run a query and have to come back the next morning to get the results of that query because of how the poor interaction between the relational database structure and the way that someone coded the query, or the way that someone logically stored the data in the relational database, which sort of gave rise to the NoSQL approaches, which are optimized for sort of different characteristics in the data, and in a lot of ways can perform faster than relational databases can. So there are a lot of products on the market, and some of these are really old. I think I have Ingres and Sybase. Sybase was actually, I think, the first marketed relational database system. Ingres was not too far behind. And there are a lot of pseudo-relational stuff, like the FoxPro databases were pseudo-relational, Access was pseudo-relational. So lots of products that are marketed out there that people call databases, and they all have, in some ways, if they call it a relational database, they should all sort of conform in general to CODS 12 rules, but they don't all do this in the same way. And so there really are differences between the products out there. So when we think about a database system, the first thing to think about really is what we do with data, and understand what of it you get with a relational database, and what of these features that you might want to do with data you don't get with a relational database, that you have to build on in some way. to the relational database. A lot of people, when they're doing a research project, they say, oh, I need a database. And so they tell a technology person that they need a database, and the technology person says, oh, they need a set of tables. Great, which tables would you like? But the person really doesn't mean they need a set of database tables. Of course they do, and they want to store the data in them, but they also need other functionality like workflow and data flow and moving data around and the ability to enter data and view data that doesn't come for free with a relational database. And so a health information system or a research information system is really a relational database with what I call application programming. It's really a relational database with a bunch of stuff on top that gives you some of that functionality that we just talked about. So for example, the ability to view or review data, the ability to enter data, the ability for a second person to perform data entry and to see discrepancies between first and data entry and be able to make the correction. That you don't get that for free with a relational database. You have to write computer programs to make it do that. Checks for data completeness and consistency, aside from the basics that you get with a relational database, which we'll talk about a little later, any of those checks for data completeness or consistency, you have to write code to do those. The ability to update data, store data, and load data. If you have just a set of relational database tables, you're actually writing SQL code to update data and to load data into the database, whereas with a program that's built on top of a relational database, you would have a user interface and a nice kind of point and click way to do some of these functions. The same with tracking data. Maintaining data integrity, the relational database does for you just fine. As long as you mean the basic integrity that we'll talk about in a little bit. Any additional relationships in the data that you want to maintain, those also have to be built in, as well as additional features to secure and report and transfer data, and especially the ability to make a record of all database changes. Most relational database systems have audit trail functionality. It is very, very difficult to get at and view and make it available to users without additional programming. So a relational database, while it sounds like, and we might have all been thinking that it's the zenith of exactly what we need for our research project, it really is not that. And we need something more in line with a health information system or a research information system or a lab information system or any of these other kind of information systems that have software functionality built on top of the relational database that provide that data flow and that workflow. So make sense? Big difference. Okay, so a really important point is what's the difference between a database and an application. And so databases that we just talked about can store data, and they can do that for any kind of software product that's out there. If you have a software product that writes reports, you might store the underlying data in a database and use the software package to write those reports. If you want to do double data entry for data for a research study, you would have sort of separate functionality for doing that double data entry, but the data would be stored in the database. The important thing is a principle called data application independence, and this is not so distant of a phenomenon in that, in what I talked about earlier, where you'd write a computer program and you'd reading data from a file and writing data to a file that's out there in some directory with your computer program, or in some other directory that you give the computer program the path to. Data application independence means that the software is engineered such that software applications don't care about the underlying data. As long as the software understands logically how the data are structured, meaning sort of what data are in what table, which we'll learn exactly what that means in about 10 minutes. So the software really doesn't care about any changes to that underlying data as long as logically they're structured the same. If you move them on a different server, if the physical storage for where that data is stored changes, none of that matters as long as the application can talk about the logic data model to that underlying database, then none of those changes impact the application. The applications also don't care about the details of the physical storage. So the ability to engineer software applications such that the application doesn't care how the data are stored is a really big deal, because number one, it frees up organizations from having their data locked in some proprietary system that they can't get access to. Back in the old days, as late as the 90s in some cases, definitely in the 80s and the 70s, if you bought a computer system, your data was in their proprietary model, and you often could not get to your data as an organization. That has changed today, and there is an expectation, a ubiquitous expectation, that an organization that purchases or licenses a software product has the ability to get to the data and can migrate data in and out of that system as they choose. So for example, before we migrated to Epic here at UAMS in the clinical environment, we had another electronic health record system, actually multiple ones. And so because of this data application independence, we had the ability to take a snapshot of that data and keep that data institutionally, so that when we decommissioned those old software products and put Epic in the production here at UAMS, that we didn't lose the history of that old data. Those old legacy data are still available, albeit with a little programming through the data warehouse. But we as an institution have them, and they are here, and we didn't lose the data when we changed software products because of the principle of database application independence. So I spent a lot of time on it, but it's really important shift in software engineering. So I want to kind of take a little bit of break and pause for a few minutes. Why don't we just use Excel instead of electronic health records in the clinical environment? Or if you're a lab person, why don't we just use Excel instead of a lab information system? Does anybody want to hazard a guess? And then I'll repeat it back in the mic so folks listen to the recording can hear. Yeah, so in Excel, the rows and columns are whatever you want to name them, and there's not connections between them unless you make those connections. In a relational database, you can formalize some of those. There are some other considerations, like for example, if you were to look at an electronic health record, there's a really complicated, in some cases, user interface where the data are entered. So in other words, can you imagine like a physician or Felicia, I'm gonna pick on Felicia, when she's giving her breathing treatments up on the unit. Can you imagine Felicia having to stop giving a breathing treatment, turn around at the computer and say, hang on, let me write some computer programming so I can chart your data? Okay, that's not gonna happen. Not.
Even now, how would if we use Excel, you know how like the Epic patients, ID badge and everything before we can even get into the charts, so how would you even access?
Yeah, exactly. So there's all of that workflow and those controls and protections that we have as a result of having Epic that we wouldn't have if we just went with a spreadsheet or just with a base relational database system. So yeah, exactly. So even though, Felicia, you will be able to write SQL code after this class, you probably still don't want to, and I don't blame you. The other things are our data flow, the integration between systems, the ability to move data between systems is a little tougher with Excel. It's really clunky. With electronic health records, you get a lot of that interoperability that you configure into the system so that when a patient comes in and it is registered, that registration message automatically goes to everybody in Epic and is seen ubiquitously by everybody in the record. So when lab results are ready from the lab, they become available in Epic so that the care team can see them. So any of that interoperability or exchange of data between systems you wouldn't get. Although the class today is about relational databases, it's really important in your mind to separate a software application that has data flow and workflow and user interface functionality on it from the basic underlying relational database where the data might be stored. Make sense? We good? All right, awesome. Okay, so I'm going to switch gears a little bit, and then we're going to start to do some exercises. So data in relational databases are organized into tables. So if you want a concrete model for what a relational database might logically look like, open up Microsoft Excel. And each of those tabs in there would be like a table in your relational database. Okay, so logically, the way that the database thinks about it and the way we think about it, data are stored in tables, and tables have names. Each table has rows and columns, just like a worksheet in your Excel spreadsheet. Tables are related to each other, and this is why we call it relational. Because, for example, if we have a demographics table, or say I'll use a lab example. So say you're in a clinical lab, and you might have a table with characteristics about the patient, and then you might have another table with some characteristics about the sample, and then you might have another table that would hold the results of the lab test that you did. But the relations between them are key, because data pertaining to one patient is stored in all three of those tables. You got data in the patient table, data in the sample table, and data in the results table. And so why it's relational is that by virtue of having a unique identifier for a patient and a unique identifier for a sample, and having the unique patient identifier in the sample table, those two tables are related, and you can connect that data back up. And the same thing for the sample and the results table. Each sample is going to have a unique identifier, and you're going to store the unique identifier for the sample in the table where you store the results for that sample. And so by virtue of that, you can connect results back to a patient, because you had the sample ID in the results table, so that connects results and sample. And then you had the patient ID in the sample table, which helps you connect sample with patient. Make sense? Okay, we're going to do some examples and draw that out so that we can see how that works. So those links that I just talked about between tables are called keys. So this is what it might look like. So let's say we have a table for some I don't know, vital signs data. We might have the bottom one, we might have the subject number or the patient number, we might have their initials, we might have a gender, we might have their weight, and we might have their pulse. And if we collected more than one weight measurement, we would have more than one row in that table for that patient. Make sense? Okay. So, but we might structure the data differently, right? If you look at the top table, we might have the subject number, the patient number, and the initials, and we may have the systolic and diastolic blood pressure and their heart rate stored in that table, or the pulse. So when you create relational database tables, you decide what goes in that table and how that data is structured. Make sense? Okay. So we're going to go over in the next two slides, we're going to go over some kind of relational database language. So a table in relational theory is called a relation or a base, relvar. And so this whole table at the bottom would be the relation. Okay, and remember, every table logically has rows and columns in it. And so a row in a relational database table, people, if they sort of use relational theory language, are going to call it a tuple. A column, they're going to call it an attribute in a relational database table. Might correspond to attributes that we talked about in the class model, all the list of things in the box on the class model, but not necessarily, because in a relational database, you can logically organize that data however you want, as long as you meet the requirements of the relational theory and of being able to link that data to formalize the associations of the data for how they match the real world. So the things to remember from this slide are a relation is a table, a tuple is a row, and an attribute is a column. We won't use that language in here, but when you see it out in your real job elsewhere, or you will run into people who might use these words for them. The important part well, one important part of being a relational database is the way to link those tables, like that lab example we just talked about. And so the way we do that are by things called keys in a relational database. And so a primary key is a set of identifiers that uniquely identifies records in a table. And so if we go back to here, the table with the subject number and the initials and the gender and the weight and the pulse, subject number would be a good, the way this is structured would be a good primary key. And I'm going to tell you that, and then I'm going to tell you, think about it that way, but that's really not the way the database is going to implement it. Relational database designers will, if something is really the primary key for the table, it will be system generated, and there will be no way to have duplicates in there. But you can logically, as we learn it and think about it, we want to think about as informaticists, we want to think about what pieces of data uniquely identify a row in a table. Because if we mess that one thing up, that is the one most important thing. If we mess that up, then we might lose associations in the data and not be able to link the data back together. Or if we're using data that have already been defined, if we misunderstand the formal associations between the tables, we might not get out what we think we're going to get when we write SQL code. So the primary key is the one that uniquely identifies rows in a table. A row is a record. A candidate key is an item or set of items that represents a possible choice for the primary key. So it may be that you might have a table and you might have more than one column that could uniquely identify rows in there. And so in that case, you would logically be thinking of one of those as the primary key, and the other one, the one that you didn't use as the primary key, but could have, would be called a candidate key. The next type of key is called a composite key. And that's basically a key that's made up of values from one or more columns. So if you actually, it has to be more than one column, but so let's go back here. So let's just say this was a community health fair, and I only have one row per patient. And the only thing I'm taking data on are their gender and their weight and their heart rate, which would be a useless health fair, but let's just say that's what it was. And I only take it once. So that means I'm only going to have one record in this table per patient. So in that case, the primary key, the way I think about it, would be the subject number or the patient number. Now let's say I was a company and I went around to multiple communities and I did health fairs multiple times a year. And I could have more than one set of data for a patient at the health fair. So then I'm going to need a composite key, because the subject number is not going to uniquely identify a row. Because if I have Mary Jane who goes to every health fair that we offer every month just to get her stuff checked, and then Mary Jane, if we do them every month, Mary Jane is going to have 12 rows in that table per year. And if we just use the subject, the patient number, in order to uniquely identify the records, and we pull back, give me the Mary Jane's patient 1, 2, 3, and we say, select all the data for patient 1, 2, 3 out of this table, we're going to get 12 records. So we won't have uniquely identified a row. So we would make a composite key. We would add a column in that table, and what that column we would add would be for the visit date. So then if we use the patient number and the visit date, then we can uniquely identify the record. You guys with me? Sweet. Okay, awesome. So that's what I mean when I say a composite key. That's what anybody means when they say a composite key. And the last is really, really, really important. To me, it's just as important as the primary key, is the foreign key. So remember in our lab example where we had the patient table, we had the sample table, and we had the result table. So if you remember in the sample table, what did we store in there? We also stored the patient ID. So in the sample table, you might take more than one, like if I'm doing needle biopsies, I might take 3 different samples from a patient. And so I'm going to have 3 unique samples that I need to identify in that table. All of them are going to have my patient number. In the case of a healthcare system, it'd be a medical record number. So all 3 samples would have the same medical record number on it, but they would have different sample numbers on it. But by virtue of having the medical record number or the patient number in the sample table, that is the foreign key that allows me to relate that table back to the patient table. So in other words, that's how I get my sample data connected back up with my patient. And then the same thing in the results table. I have the sample identifier in the results table. So for sample X4321, I have a result negative. And I need to connect that negative result for sample X4321 back to Sally. Okay, so I'm going to connect it. I'm going to say that result was for X4321 sample. In my sample table, I have X4321 related with that patient's medical record number, and that allows me to connect it all the way back up.
It's basically a merge.
Exactly. So you're a SAS guy. Okay. So yes, they are merge variables. Does anybody know what a merge is? Okay, so in here we're gonna talk about joins in a relational database. A join is like a merge in SAS. It's when you take data from 2 tables, or in this case, our 3 tables. Let's say I got sick of having to chain all the way back and all the way forward to get to my data every time I looked at it. And I wanted one table with the patient number and the sample number and the results in one table, which means I'm gonna have multiple records per patient, possibly per sample in that table. Then I'm going to do what's called merge them all together. I'm going to use those foreign and primary keys in order to link all the data back, and that would be called a merge in SAS. Make sense? Okay. And I think I saw a question. I heard a question come up, so hang on just a second. So yeah, Hoda, it would be like I think sample numbers are close to an accession number in there. Is there in the lab environment? Is there more than one accession number per sample, or is there always one accession number per sample? That must have been a complex question because Hoda is still typing. Okay, so one accession number for each sample, and then also Hoda says an instrument number in the lab, because you want to be able to connect the result back to what instrument it came from. Probably, I'm guessing, for calibration purposes and maintaining the ranges. So Hoda, accession number would definitely be a key that you would utilize in a lab information system. Thanks for the question. Okay, so those are the keys, and as we think about how to combine data across tables, or probably, just as important, how to maintain associations in the data. Because as an informaticist, if I was going to work with somebody to design a system, I would never want to not store an association that the person needed. So if I was building a system for Hoda, and Hoda needed legitimately to be able to connect the results back to the patient, then I would have to make sure that I stored data to formalize those associations from the patient to the sample, to the results, also to the instrument, Hoda just said, in order to maintain those formal associations in the data. And so one of the biggest mistake that I make, that I see people make as researchers, that will come when they call me up and they say they've had a data problem and they need some help, is that they have made changes to their database, or they didn't store some of those associations that they needed at the time of analysis with the data. One of the most common mistakes, and it's because nobody trains researchers in the relational data model. So they don't necessarily know to think about those things. So that's why we spend time talking about the keys. I'm also going to take a little bit of an academic dive into set operations, and this is, you don't need to be an expert in this. You need to know what the words mean, or you need to know what you're looking up when you go to look up the definition of the word when it comes up in conversation 3 years from now and you have legitimately forgotten it. So set operations are what we use when we're working with relational databases. The combination of set theory in math and the rules that define a relational database are what enable all of this to work. And so the first word is a partition. In set theory, a partition is something that you get when you divide some set, meaning like if my kid had Matchbox cars and my kid had 40 Matchbox cars, that would be the set. And I'm going to partition that set into cars with 4 wheels and cars with other number of wheels, whether they fell off or not. So by partitioning that, I'm setting up 2 mutually exclusive groups out of that initial group. Does that make sense? Like a what? Yeah, exactly. I have discretized the data, exactly. And the key to this is they have to be mutually exclusive with no overlap to be a valid partition of a set. And so if I say instead that I want my kid to put all the 4-wheel cars in one box and all the cars with more than 4 wheels in another box, I've defined a partition, but I might have left out the motorcycles or the tricycles or cars where wheels have fallen off. And so in that case, by telling the kid that, I now have I have a partition with 3 parts. I have the 4 wheels, I have the more than 4 wheels, and I have the less than 4 wheels. Make sense? So when I say partition, I mean clean partitioning of the set. So these are all of the logical possibilities. And so what these are ways of mapping in set theory. And you can't see them very well. Okay, hang on. I'm going to have to exit out so you guys can see this better. Still not showing up. Okay, hang on just a second. All right. Okay, the ones that I'm blacking out, these had, the X's were too faint to see. These are combinations that you would not really use in reality. But these are errors that people make when they're storing data. So which is why I've had them more faintly marked out, because do they exist in the wild? Yes. Are they legitimate logical combinations that you would want to do with your data? No. Okay, so the ones that we're going to look at 4 types of mapping, which is bijective, surjective, injective, and then the definition of a general function. So a bijective mapping is basically a one-to-one mapping. And so when you have the initial set, the gray balls, that where every gray ball maps to something in the target, which are the open balls, then that's called onto, because you're able to map all your gray balls onto the other set. And so the 2 types of onto mapping are bijective and surjective. The difference is that surjective is a many-to-one. So in other words, when we talked about data reduction with discretizing data, we're reducing the information content. This is exactly how the information content gets reduced, because you have 2 things that are unique and distinct in reality, but in the database, you're storing them in one category. So as far as the data are concerned, you have lost the distinction between those 2 things. Make sense? And so the set theory word for that is a many-to-one mapping or surjective mapping. And injective mapping is where there's something in the target that's not mapped to, so that's not an onto situation. And then the general functions, all of these are general functions. The definition of a function is that it is a mapping of one thing to another. And so that last one that's why I just have that labeled general function, because it's not onto, nor is it one-to-one, because you're having the information reduction going on, and then you're also having one in the target that has nothing mapped to it. Make sense? Mm-hmm. Yeah, so an example for surjective, say that in the database, just for gender, say I had male, female, and I had some people that put transgender, and I had other people that were unknown. And in my database, I'm a blockhead, and I just built it as male, female. So the unknowns and the transgender would have nowhere to be mapped to. And so I would have to map them to something. Or maybe I'm not a complete blockhead. Maybe I have, in my database, maybe I have male, female, and unknown, and I take the unknown in the initial data and the transgender and map it to unknown. So I've lost that detail in the data. I've lost that ability for the data to accurately represent the reality of the situation. Make sense? Awesome. And then these other ones around the edges, are basically just sort of problems that you might find in the data. So where's this? Yeah, I'm gonna, hang on, I'm gonna take this one off. So if we look at this one, in this particular box, well, in everything on the one-to-many, this last column here, I am creating information. Can anybody tell me why I'm creating information, or why I would call it that?
Well, I see that one of the gray balls is going to 2 new records. So something about that is being split, or something new is creating individual.
Yeah, exactly. Yeah, so say in my initial data I had an other category. Okay, and I took the other category and I mapped it to 2 different things. So if I have 0 information about what was in that other category, it's just logically nonsensical to split it out like that or create information. Now, if I have an other specify field and I go back after the fact and I kind of try to code them, say there were, I don't know, say there were different eye colors. Let's say there's gray and there's dark brown and light brown. And in my initial data, I just had blue, green, brown. And then there were some people that checked other because they had gray eyes or because they had light brown or dark brown eyes and didn't feel those were accurately represented in my initial list. So if I go back and use the other specify field, I might be able to separate some of that data out. It's of questionable validity depending on the consistency with which the other specify field was collected and the confidence I might have in that. But this, that is done a lot. So you're sort of, in that case, if you have the other specify field, you wouldn't be creating information. But in the case where you don't have it, you might be creating, this represents a logical impossibility because you're creating information where none existed before.
What happens if, like, just for your example, the iPhone in an other box, like if they didn't just, how would you code that, or how would you, would you create something totally different, like they would have like 4 or 5 rounds, 5 Paisley?
So basically, in the way it's usually stored is that there, for the variable eye color, there's a pick list or options for it, and other would be in that pick list, and then there would be an other specify. If in fact they check the other, then they would put it in there. So the other would be one of these, will be that gray ball at the top that's mapped to 2 different white balls in the case of our dark brown, light brown, and gray eye people. Make sense? Did that answer your question? Okay. Okay, so so look back here if you need to know what the terms are. If you're talking with folks about mapping data, you may hear these words come up. So there are, and I'll go back to the screen mode. There are 8 relational operators that you, so this is sort of a high-level way to think about what you're doing when you're executing SQL code on a database, when you're going into the database to get data or look at data. So one thing you might do is union the data. That means you're just combining them. So you're combining the rows from 2 tables or the tuples from 2 relations, and removing any duplicate tuples from the results. So this is in, a union is an OR. It's anything in this table or that table, inclusive of the overlap between them. The exclusive OR, this is not exclusive OR. Exclusive OR means you wouldn't have anything in there that was overlap. So a union is just an OR with the duplicates removed. A lot of systems have a different kind of query that you can write that will allow you to keep the duplicates in there. It depends on how you do it in the syntax. An intersection is the AND. That means that you're producing a set of rows that 2 tables have in common. And we're going to see, I have pictures of all these to help. The next example is a difference operation, and it basically produces a set of rows from the first table that don't exist in the second table. You could have a Cartesian product, which is basically, there's no restriction, and it results in every row in one table combined with every row in the other table. So in other words, this is something you would not want to do. So we had back in my, where I used to work, we were managing a large international clinical trial. There were about 3,000 or 4,000 patients on it. And we were managing the data on the pharmaceutical company's platform. So we all had access to log into their system and do the work. And one of my folks, a newer data manager, executed a SQL query on the tables, executed a Cartesian product with it was something heinous. It was like the audit trail for the lab table or something. It was like this huge table. And about a day or 2 later, somebody from the pharmaceutical company calls up and says, "Do you realize your query is still running?" Because they had done something logically that they did not intend on doing, which is combine every row in this table with every row from this other table. There are reasons you might need to do that in order to get mathematically to an end product, but sometimes it's just something that you really don't want to do. Another type of relational operators is a selection or restriction, and we're going to be learning how to write select statements. So that's basically what you're doing. It basically it retrieves rows from a table, but it retrieves only a certain number of rows, only the rows you want. So if we were thinking back to our table with Mary Jane's community health check data, and we wanted only Mary Jane's data, I would select all the variables from the table where the medical record number equaled Mary Jane. So that selection just returns a subset of the records from the table, which is in fact a partition. You've partitioned that table into the records meeting your select statement criteria versus all the ones that don't. A projection is another kind, and it basically extracts only the columns that you want from a table or a set of tables. A join is we talked about earlier with the merge. It's a way to look across tables, to look at data, some data that's in one table and other data that's in another table, and you've joined them together. So in other words, I want all the lab results for patients with blue hair. And in order to do that, I have to join the patient table to the sample table to the results table so that I can then select from that data just the lab results from the patients with blue hair. So in that case, I've done a join to get the tables together. I've done a selection because I'm looking at only people with blue hair. And I've done a projection because all I want are the lab results. Make sense? Cool. Okay. Yes?
What's the difference between join and join?
So in a join is where you're taking the tables and you have different options for doing the join. When you do a union, you're taking the rows from one table and setting them right on top of another like this. Thump. Well, from in?
And append?
In SAS, it would be set. But I don't know what append, is it from another syntax? Or it may be an alternate way to do a set in SAS. So in other words, if for a union, say Sharab and I have data again, and we have lab data. I have it for regional program clinics, and Sharab has it for UAMS clinics. And we get together and say we're going to put the lab data together, and we're going to do some public health work with it to do some, I don't know, cholesterol control. So I'm going to go to Sharab and say, okay, you got your stuff in a test name and a result column. He's going to say, yeah. I say, okay, I'll put mine in that same structure, and then we're going to take yours and mine, and we're going to combine them together. Okay, yeah. Yes, same columns. Yes, exactly. So for a union, you go like this. For a set, you go like that. Or a join, you go like that. Yes, you're right.
Join is in general to join tables. It has categories, inner join, outer join, left join. So that's your
We'll go over those types of joins, Sally. Okay, we'll go over them. But for now, a union, vertical, join, like two separate tables. Okay, and then a division is basically, it's kind of the opposite of a Cartesian product. And so you're looking for the rows in one table, you're using them to partition a second table. So like you're saying, for the rows in this table, I only want this particular data in this other table. And so I don't think I've ever coded a division before. Do you guys use that, Sharab, Mahanez, and what you guys do? Using kind of the set in one. I'd probably do it with a join, try to get it with a join, but. Okay, so here's the pictures. So restriction, remember that's our select statement. So we're picking only certain rows. I want only the people with blue hair, or I want only the lab results for Mary Jane. So instead, so this is these are our little database tables, these boxes. So when I do a restriction, I get a shorter table. So I'm selecting rows for a restriction. For a projection, I'm selecting columns. So I get a narrower table. For a union, I stack them on top of each other, and I get a longer table. For an intersection, where I'm doing an and, I get a shorter table, or one of the equal length, if they're both have the exact same records in them. Because remember, an intersection is you want the records that were in one and also in the other. And then for a difference, you want one that's in the left-hand table and not in the right-hand table of that equation. So for example, you might have records, you want records that are in here and not in here. So that gives you a shorter. And then the last operation is the product, and that's when you get wider and longer tables. And so the main ones that's important to know for these, really that we're going to do anything with, are restriction and projections. That's just your basic select statement. We will go over what the joins are, and you may be able to code a join or two, but these are the main ones. So now we're going to talk about, so these are the joins, Sally. So as Mahanez was saying, that was you, right, Mahanez? Sharab, I'm sorry. So as Sharab was saying with the joins, there are different flavors of joins. So the first one at the top is an inner join, and that means you only want the data that's in both tables. So first table has patient Z, X, and W. Second table has Z, X, and U. If I do an inner join, then I'm only going to get a table, the results out with Z and X in it. Make sense? And so if I do a left outer join, that means I'm going to get the result of the inner join, the rows that are in both tables, and the one that's on the left. So in other words, I'm going to get everything plus the ones in this table that don't have a match in this other table. So my first table has patient Z, X, and W. My second table has Z, X, and U. and I do a left outer join between those two tables, I'm going to combine the records of those two tables. So I'm going like this. Notice all the products here, the end results are longer because I've taken the records and put them together. So I have all the records from the Z table, all the records from the X table, and the W table, but I don't have the U because I did a left outer join. And so thus from where W was not in the second table, in the right-hand table, I'm not going to have those columns for W, which is why it says null, null, null. Make sense? Okay. A right outer join is just the opposite thing. It means I've got the Z, X, and W on the left, and then on the right-hand table is Z, X, and U. Since I'm doing a right outer join, I'm going to have the records from Z and X and U, and I'm not going to have any W's in there. And since the right table didn't have the same columns as the left table, any of those from U, those columns, they're going to be null because we didn't have any U in that left-hand table. And then a full outer join, if you're looking for stuff that's missing from tables, oftentimes we want to know people who have a demographic record but who have no medication reconciliation history or no lab values. And we also care about if a patient has lab values, we don't have a demographic record for them. So we'll do a full outer join and we'll look at the stuff at the bottom. We'll do that to show us what's in one table and not in the other table. So those are the different types of joins. Make sense? Okay. Normalization is well, I'm going to say it was a big deal in relational databases, but it kind of still is. The issue is that sometimes a long skinny table is more efficient for some things, and other times a short fat table is more efficient. So if I'm going to write reports on data, man, I don't want to have to be joining 8 different tables, or in Clarity where there's 17,000 tables. Right. Yeah, like I really don't want to join all those tables together. So I'm going to look to my colleagues, Sharab and Mahanez in the warehouse, who have already done all those joins for me and have given me something flatter that's easy to query against. So for reporting, you generally want a flat structure. If you're using a statistical analysis package like SAS, I'm guessing SPSS and Stata are the same way. When you use those packages, it's lovely if you have one data element per column, because then you can just use the procedure on the table and your column statistics are good and they mean something. Whereas instead, if I had something more normalized, which means long and skinny, so let's say for vital signs, if instead of a column for systolic blood pressure, diastolic blood pressure, and heart rate, I had only one column for results and one column for a name of the test. So if I ran it through a statistical analysis package and said, give me the column statistics, on the flat table, it'd be good. My column statistics would be the average systolic blood pressure, the average diastolic, and the average heart rate. But if I did it on my long skinny table and got the column statistics without adding some other code in there that said only look at these ones, then I would get an average of that column, but it would have systolic blood pressure, diastolic blood pressure, and heart rate all in there together, and it would average them, which would be meaningless.
You have to partition the data by generating a number.
Yeah. Exactly. So what Robert was saying was that you have to write code, you have to write computer code if you're long and skinny. So for reporting, short and fat is good. For some of the more transactional work that's done with a relational database, long and skinny is more efficient. So for a system that's used for maybe, I'm going to say online commerce, but I doubt a lot of them are relational anymore. They would tend to be structured long and skinny to store all the data. It would be easier to add new information in there and then easier to manage. But then for reporting, they would flatten it out to a different structure. So normalization is the process of going from a very short and fat table to a long and skinny table by eliminating the redundancy in the data that exists in the table. And so we're not going to normalize things in here. when I used to teach this, we had a Lego database. So we'd make a big lab table that was short and fat, and then we'd take it all the way down to second normal form with the Legos so people could see. But you don't need to normalize anything now. You need to know what normalization is, and it's the process of removing the redundancy in the data and making a very long, skinny table. So what I mean by redundancy, say I've got my vital signs table, and I have diastolic blood pressure, systolic blood pressure, and heart rate. And so let's say I'm the community health fair thing again, and people can come once a month. And so for every row in there, I'm going to have the patient number, and I'm going to have all their contact information, and I'm going to have their visit date. And then I'm going to have those three little blood, 2 blood pressures and a heart rate. And so what that table looks like is I've got all this repeated contact information for these patients and all the repeated patient number all over again and stuff. And so if I want to go to a more long skinny table, which might have a test name and a test results, like we might store lab data. And so the test name column options would be diastolic blood pressure, systolic blood pressure, and heart rate. Then I have less of that redundancy in there. So it's the process of going from short and fat to long and skinny. Stored procedures are another thing that we do with relational databases. A stored procedure is executable code. For example, whenever we get a new record entered into the database, we want to check and make sure that certain important data values are present, or else we don't want the record to be written to the database. Then we might write a stored procedure that checked it before it was submitted to the database. So that's what we mean by a stored procedure. So we're going to draw out some data tables. So let's just look at this at the demographics table. And I don't think I can leave that on and make that go up at the same time. So everybody whip out your sheets of paper. All right, so if I want just a flat table with one column per data element, I want all y'all to kind of sit and think about how to structure this. And Sharab and Mahanez, I'm going to ask you guys to walk around and help people, since you guys could do this in your sleep. Put the data on this form in a table with one column per data element. And so I'm just going to, so for here, there is a little trick of a question on here. So where it says check only one, that's a data element. Where it says check all that apply, that means they could check more than one. So in order to store that kind of more intelligently, I would need one data element for each choice option if it says check all that apply. Does that make sense? Okay, so if under the race field, say that I was of mixed ethnic heritage and I was part black and I was part white. So, and on my form, I'm going to check black and I'm going to check white. But in the database, if I have it just one data element, then I have to put black and white in the same value field. And so I can't compute on those separately. And so what I'm going to do so that I can write computer code on those is I'm going to make a column for each of the choice options under race. Does that make sense? Yes, exactly. Because if otherwise, what you would have to do is say for me, you would have to do, it would say black, comma, white in the same data field. And then because anybody might have any combination of these in their race, in order to use that data, you would have to write computer code to address each possible combination. Okay, whereas if you store them each in a column, it's much more easy to compute over if you have a column for each of the choices. So then, I can easily count the number of people in each category, and I can count the number of people that with more than one category selected. Make sense? Okay, so everybody draw out your table, and I'm going to run and get a drink of water. I'll be right back. Since we're in here for so long, if you guys need to like get up and go take a break, we can either do that now, or if we're talking, you can still get up and go take a break.
Speaking of David. Zero.
So you know, like,
I didn't need to demographic scale, so it can be so short.
Some. Commas.
Zero.
Green. Oh, well. Regress. Regress. Inadequate.
I feel very strong.
For this one, for patient identity, will be a auto-generated column, right, for each and every patient.
Yeah, so this is a section from a clinical trial form. So there would be a patient number on it for the ID. Thanks, Mahanes. That's important. You guys need more time, or are you good? Okay, so how many columns did you guys have in your table? It not counting the patient identifier, which we of course would want. Okay, excellent. So, so good, you guys have the hang of it. Okay, we're gonna work some more examples, but a data dictionary basically is sort of what you guys just did. You guys made a database table for the demographic information. What I call the table name, this is just a convention that we used to use at another place in order to specify how we wanted the data stored. We'd put the column names in red, and in the brackets, we would put the data type and or name of the pick list that we were using. And the type 1 means 1 record per patient for the whole study. So for the demog table, you guys would have your 8 columns. This just happened to be what we named them. It doesn't really matter what you name them. So a data dictionary basically is getting that information out. So this is a data dictionary example for our demographic column. So if you went to somebody who was managing a database, so let's say that I took this to, I'm going to pick on you guys, Sharab and Mahanez, is that okay? Okay, so let's say Sharab and Mahanez built this database out for us that we just specified. So then we might tell our friend they can use the data for their research study, and our friend would call up Sharab and Mahanez and say, hey, can you guys send me a data dictionary for that table so I can see how the data are formatted. So Sharab and Mahanez would send them something that looks like this. So in a data dictionary, it basically defines, it gives you the name of each column, the data type of the data, whether it's like in SAS, it would be numeric or character. In Oracle, it can be a number, it can be a date, it can be a varchar, which is a variable length character, which means if my character field, say it was a name field or something or an other specify, I would put varchar 20, that would allow up to 20 characters in the field. But if the response was less, then it would only store that less amount in there. And then the data dictionary would have a description. Ours used to also have the name of the pick list for enumerated data elements, for the discrete data elements with a pick list. And I think I saw a ding or heard a ding. So I'm going to go check the comments out there. Yeah, Hoda, thanks for the question. So Hoda asks, would we put the day and the month and the year in the same column? So there are reasons to put them in the same column, and there are reasons you might not want to put them in the same column. So when we collected data, we always stored the date parts separately. So I would have a separate column for day and another one for month and another one for year. And that's because if a person didn't know the day, but they knew the month and the year, I wanted that partial data. And if they didn't know the month, then I still wanted the year, because then I could maybe impute data in there. And so in some systems, storing the dates as parts is the only way that you can easily get partial data like that. Often if you store it all in one column, and if you say that it's a date field, then the system won't accept it unless it's a complete date. It depends on the system. All systems are going to handle that exception differently. But in the other factor that might play into that is if in fact you wanted calculations to be done on that at the time of entry, sort of real time. So in other words, when they put the date of birth in there and you wanted it to calculate their age, and then you wanted it to check and make sure their age was over a certain limit to make them eligible for a study or something, then you would want all that math to run real time. And so if you do that real time, if you have the data stored as a date variable type, then that date is accessible to the system immediately and can run math over that. If instead you've stored it as date parts and you need to do date math on it, then you need to combine all the parts into a date to do date math. And if for any partial data, you need to handle the imputation or the exception of how you're going to handle the missing. And all of that computer programming needs to be in place on the user interface at the time of entry. So depending on what you're doing with the data you're collecting and how you want to handle it while the user is entering the data, you may make a different decision about whether you would put those parts, those date parts, in the same or in different columns. And it's really, there is no right or wrong answer. It's what solution is best for how you are processing the data. Make sense? Okay. Yep, thanks, Hoda. Okay, so that's an example data dictionary. So what I want to do now is, okay, so given your demographic form, now that everybody already knows the answer, so if this was for a study and a patient comes in for the baseline visit, and your DEMOG table just has one row of data per patient, how many records will exist in the DEMOG table for that patient? Does everybody understand that?
Is that just for that? It's one because of that one visit.
Yep, because here, if we go back to our form, so this is our demographic form for the study, and we're stuff that we're only going to fill out once per patient. We're not going to make them fill it out again if there's different visits. So that tells us it's just one row of data per patient, and we've structured it flat, right? We've made a column for each data element, which also tells us it's one row. If instead I had structured it as long and skinny, and so if I had a column for patient ID, and then a column for question and a column for answer, then I would have more than one record per patient in that table, right? Because I would have, if I had one column called question and the other column called answer, my questions would be date of birth, sex, ethnicity, race, race, American Indian or Alaskan Native, race, Asian, race, Black or African heritage, race, Native Hawaiian or other Pacific Islander, race, white. So I would have a row for each of those if I had structured the data in that way. You guys want me to draw it? Oh, you good? Okay. So given that we have structured it in this flat way, the answer to our question is one record per patient. But we certainly could have structured it such that we would have had more than one record per patient.
You only have one ID number per patient.
Yes, yeah.
But using that flat way, it's not easy for researchers because you have to convert it to vertical way.
I use flat for 99% of my research.
Yeah, flat.
Yeah, but you have to manage this data. You have to transport this data. You can't use like it's vertical, it's horizontal. You can't use it there.
Most researchers prefer horizontal.
I don't want it in columns, I want it in rows, because then I can progress as observation. For that reason, I do.
It's not the same time.
Yeah. So in general, the statistical packages work much more easily if there's one column per data element, flat. Because in SAS, they will call that proc ready. So say in SAS, if you want descriptive statistics, you're going to use a procedure in SAS called proc means. It's like a subroutine that you call, for those of you who aren't SAS programmers. And so if you wanted to get the descriptive statistics on your SAS data set or your table, you would structure it one column per data element and run SAS over it and say, proc means from this table, and then it would calculate those descriptive statistics for every column. It doesn't know what's in them, it doesn't need to know. And you know that because you've given it a data set with homogeneous data in the columns, that the descriptive statistics are meaningful to you. So in other words, you get average systolic blood pressure, average diastolic blood pressure, average heart rate. Whereas instead, if I had structured it question and answer, 2 columns in the table, the first column for question, so I would have patient 1 systolic blood pressure, patient 1 diastolic blood pressure, patient 1 heart rate.
I mean that I have patient 1, okay, but first visit, blah, 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 blah. Second visit, blah, blah, blah. So it will be flat. These things I can't run it directly. I have to manage these data. That's what I meant.
So in most systems, it's the opposite. In most systems, it's easier for the user to manage if it's more flat for research. But for an IT person transactionally would generally prefer more stacked, because say if I have a table that's question and answer, and say somebody adds 2 new questions to my form. Holy crap, man, if it's in a flat table, then I have to add those columns to that table. I have to change my database. But if it's in just 2 columns, doesn't matter. I just add that permissible values. So I can just add the new data in without changing the number of columns in the table. So it's from a database standpoint, it's an easier change to make that way. Okay, so now we are going to talk about structured query language. And Sharab and Mahanez, do you want to try to walk around and help people install Postgres and the data while I'm doing the next few slides? Could you do that? So if you have a computer with you and you would like to install Postgres and some data so that you can write structured query language, huh? So Sharab and Mahanez, they have an easy way to do that and are going to be walking around and helping you guys while I'm talking about the next few slides. And then they've got some example queries that you can run on that sample data. Okay, so
9.4?
Yep.
Okay, so structured query language is SQL. I think it initially stood for structured query language, but now I think it's officially like one of those acronyms that doesn't stand for anything. It's just SQL. And so SQL is basically the language that you use to access a database. So it's how you reach in and pull data out and how you manipulate data. SQL is a standard. It's a standard by the American National Standards Institute. Sorry for the typo on the slide. So SQL is an ANSI standard. So if you, in that one of those first slides that had all the different little logos for all the different database systems available there, if you wrote SQL code using the ANSI standard syntax, your code should run on any of those databases. However, the database products want to distinguish themselves and differentiate themselves in the market. And so those products build in extra functions and extra special stuff that you can do. And so what you end up with is each system supports ANSI standard SQL plus all the other crap that they developed that help you utilize their system more efficiently. So if you stick to the ANSI standard, then your code will run on any system. When you depart from that, then your code is less portable to another system. Make sense? Okay. Also, if you do use SAS, if you're a SAS user, you can use ProcSQL, which is basically running a procedure that allows you to just write SQL code rather than, say, SAS data step programming or something like that. So SQL allows you to access the database. You write what's called a SQL statement or a query against the database. We're going to do some, which is so cool. I remember the first day I started executing SQL code against the database, and I was so happy because I could finally look for problems in the database and look for things that I thought were problems and see if they were really that way in the database or whatever. So it was like new superpower that I had because I could write SQL code. SQL allows you to retrieve that data from the database, to look at it. It returns results to you, meaning the data that you selected with your query. It allows you to insert new records in a database, delete records from a database, and update records in the database. So for this reason, if you are lucky enough to be able to get access to a live database, they're probably going to give you select-only access on the database, which is read-only. And they're not going to give you any of these other privileges to allow you to go to the database tables on your own and change the data in the database. Because usually today our systems used in research and clinical settings have user interface where you enter or import electronic data and where you can change or make updates to that data. So there are different sort of parts of the SQL syntax or the programming language. The first is data manipulation language, which people just call it DML, and you can insert, update, and delete records. There's data retrieval, which is just select statements. If you want to, you also use SQL in order to create your database to set up the tables. So like when you install Postgres and turn it on your machine, like it's a blank screen probably, or may have a fancier user interface, but there are no tables in the database. You have to set up tables in there, which Sharab and Mahanez have come ready to help you set those tables up really quick. So what Sharab and Mahanez are doing in order to make those tables in your database, they're executing DDL or data definition language that instantiate those tables in your database. So the functions that DDL allows, you can create a table, you can alter a table, you can drop a table, you can rename a table, or you can truncate a table. By truncate a table, I mean it's like you open the hatch door at the bottom and let all the data out when you truncate a table. So the table itself, the place that you created in the database where you're going to put the data stays there, but when you truncate a table, all the data is gone out of there. So that's data definition language. There are transaction controls in SQL which allow you to commit or write something to the database to roll back, which is a lovely, cool function. So we had, this is back where I used to work a long, long time ago, we trained all the data managers, this was our first training session, and trained them all how to write SQL code against the database for research studies that they were working with. And we were using a software system to do that. And they went in there, and this one person wrote the SQL code, and she forgot to put a select criteria in there. And so she was updating the date of birth for a patient. And so she put the new date of birth in, but she didn't restrict it to just one patient. She didn't put the patient number. So it changed every patient's birth date in the database to the same date. And that was committed on the database that ran. Fortunately, because she had been to the training, she understood exactly what she had done right immediately after she had done it. And she stood up and she told all the other 150 people on the floor entering data into the database to stop entering data. And we were able to roll the database back pretty quickly and recover. But that's what we mean by rollback. We mean to go back to a prior point in time before she had made that unfortunate little mistake with the data. Most relational database systems now have rollback and point in time recovery, so that is possible. It might be a pain in the butt. You might lose some work that had been done since the last save point, but it is possible. And then there's data control language, which involves stuff like granting and revoking privileges to the tables on the relational database. Some allow very fine-grained access to the rows on the database too. It depends on the system. So when I say structured query language or SQL, this is all of SQL. When the most people that use SQL use just that top one up there, just a select statement to go in and look at the data and read the data in the database. And so just an example of data definition language, drop tables. Have you guys seen this cartoon? So I thought that was funny. I think the cartoon is called Bobby Tables or something like that. Okay, so when you are specifying a relational database, or when you're telling somebody what you need in your database, you're going to do what we did on that demographic form. You're going to name the table. We named it DEMOG. You're going to tell them what the columns are in the table. You're going to tell them what data type each of those columns need to be. And if it's an enumerated variable, you're going to give them a code list for what goes in that column. You might also tell them some other stuff, like whether it's required or not and stuff like that, but required for you might be different than required for the database. I don't think I've ever made anything required in a database table except the primary key that the system itself makes required. That's because if you tell the database it's required, the database won't accept the record unless it's there, it's populated. So required for us for research means we would like the data for the analysis. It does not mean we want the system to exclude anything that does not have the value in there. So this is some of the information, the main information that you would need to specify to somebody who is building a database for your research. As an example, we did a query recently to pull out information from the UAMS database on HPV vaccinations. And we're taking that data over to the health department, who gets it on a transactional basis per record. And we wanted to see how complete our vaccination data was in the state registry, because the data is required in the state registry by law and the vaccination registry. So we took all of our data and we had to tell the programmer exactly how to format it when the data comes out. So we needed to tell them what we wanted to name the file, not the table, but the file that came out. We needed to tell them what variable names, what column names needed to go in the file, which rows to select in the file, for which patients we wanted the data, and then the data type of any of the variables, as well as any code list. Although for the code list, we accepted what was there, so we didn't make any new ones ourselves. But just a recent example. And so importantly, SQL is a syntax. And so if your syntax is not exactly correct, meaning maybe you don't have closed parenthesis in the statement that you write, or you don't do the syntax correctly, your query won't run. So computer syntax is very exact. It's not like natural language, where I can kind of describe it to you and you know what I mean, so you can go do it. It has to exactly be explicit. And if it's not completely accurate, then the computer will not do what you think the computer is doing. So Shirab and Mahanez, can you guys get the Postgres?
I need email address and the solution steps.
Oh, okay, let me let you come up here and do that. Yeah, so ProcSQL. Yeah, so ProcSQL and SAS should accept that. It should accept ANSI standard SQL. SAS might have other things that it will allow you to do in there that are in addition to the ANSI standard, but if you stick with ANSI standard, SAS should accept it. Okay, so everybody that wants the Postgres, I need you to call out your email so that I can email it to you.
Oh my gosh, 427 unread messages.
Yeah, I get over 100 emails a day. And like today, I'm back-to-back solid in meetings, no time in between. There's absolutely no way I can get those things answered. But some of them are crap, like, box updates. Like, I don't care what people updated in box. Okay, so how big was the file, Shirab?
The database file is 9 MB, so total email size will be like 9.5.
Okay, you may need to email it to people directly, because I don't think I have that much space.
It's the first email.
Oh, this is how it came.
Yeah.
Okay, I'm going to try to send it. Okay, so who Who wants it? Okay, Kat. Okay, Kat, I'm sending it to you. Hoda, I'm sending it to you. Okay, who else in here? Sally? Ali? Hey, LB. Is this you? Okay. This new? Okay, Jan? Jan, do you want it at UALR or here? Okay. Okay, Felicia? Anybody else? Amy? I'm sorry, Amy. Are yeah, you're a student. You're on UAMS. I don't think I've emailed you here before. This one? The middle one? Okay. Anybody else? Okay. All right, guys, here it comes. Big file. Cross your fingers that I have enough space to make it send. Ha, it went. Yay. Okay, now hang on and let me go address the dings and see. Okay, yeah, I got to go send it to all these people. Okay, so let's see. So, okay, Rebecca needs it, Mitra, and Michael. Okay. Okay, guys, hang on, it's coming. Whoops. Oh, how did that happen? Michael. Mitra, do you ding if you want it on your UAMS? Okay. Oh, you do want it on your UAMS. Okay. All right, I'm just going to go double check. Okay, UAMS, gotcha. Just wanted to make sure before I send something with 9 megabytes. Yeah, it might not, Mitra. Okay, did I miss anybody? Okay, awesome. Okay, so Sharab and Mahanez, I'm gonna get a drink of water. Can I get you guys to, can one of you come stand up here in the case of dings and answer questions? So the Sharab, the chat is right here, and the questions that come up from folks doing it at home will just pop up in the bottom of this list. Okay, so just do whatever. If it should stay active because that's up.
show for breath.
Are all you guys good? Okay.
Let's do that. What do you self here? Where do we go? Oh, okay. Cancel. It's already solved. Now go to your application.
You guys good?
Yeah.
Okay. Sharab, is there something different that they have to do to import the data in there? Oh, you sent it all together.
Yes.
You're the man. Okay. Okay. So I'm going to go over some. Let me just see how many. So there's about 10 slides with some examples of SQL syntax in them, and then I'm going to let you guys go to town on that example database. So this, I think for this week, we can count this as the lab. I will put up a quiz for the week. The quiz will be some of the conceptual questions from the first part of the lecture. There might be a question or two about ER diagrams, which we'll go over after we get some hands-on to get our brains to get a little more active. And then there'll be questions about I give you an example form, and I ask you if you structured the table 1 column per data element, how many records would be in it under the certain situation. So for you to understand how the data elements on the form translate into a database and how those different structures might work. So what we were doing earlier in the class. And so that'll be the quiz. So there is no lab to turn in this week. I've heard from some people that they were pretty overwhelmed, and a week or two without a lab would be good for them. So yeah.
Maybe it was just me, but quiz, there was quiz 7. Anyone else missed that? I took it.
Yeah.
For some reason I did. That wasn't as big. It wasn't the same quiz.
Yeah, so quiz, first of all, the week was long, and so there was a lot of, we had to scroll to get to it. But when either there was a date in there that I didn't see when I made it active and it turned itself off when it passed the date, or I never checked to make it available. And so somebody, I forget who, somebody emailed me and said, I can't see the quiz, fix it. So it is fixed now. You should be able to see it now. If you can't, let me know.
No, I didn't finish it, I'm all
Oh.
good, so.
Okay.
And you were doing the diagrams, you gave us additional time.
Yeah.
We had an ontology diagram today, correct?
Yep,
Okay,
for Matthias.
right, and so that would be the second.
Which week was ontology?
Okay.
Okay, so that will be due this coming Sunday. Unless you guys, if you need more time, it's okay. I mean, I don't want to make it so that all the work like piles up and in the last week of the class you're going crazy trying to catch up on everything. But if you need more time on something, just email me. Most people in here work full-time or are either full-time students in other programs. So it's not a problem if you guys need more time.
And as a question too, at what point do you think we're gonna get the grade things also filled in the grade books and figure out where the LX can get?
Yeah, so your quizzes and the labs that are graded as multiple choice questions should already be in there. That I'm very behind on the discussion forums and have sort of left them to try and catch up on some of the labs that weren't that way. So those are unfortunately I'm getting to them on the weekends. And I know it's frustrating if you're panicking about it or you need to see the grades to feel more comfortable. Let me know. I don't want to make anybody panic. If you're pretty certain how you did, then that's fine. But if you're panicking, let me know and I can go in and try to prioritize, whoever, if you're concerned about it. Because I get as a student, it's concerning if the instructor is behind on grading. Yeah, no, you're not. I'm not leaving you out. Okay, so this week, no lab, but there will be quiz. Okay. All right, so the way structured query language works is basically these 4 words in red are the words that you use to interact with the database. So a basic select statement to look at data in the database, you're going to say select some things from the database from which tables, where they meet certain requirements. So I'm going to say select a certain number of columns from a table where the people have blue hair or where the patient number is above 80 or something. And then I might have them order the results. When you order by, that orders the results you see. It doesn't order the data in the database because the data in the database are stored however the database stores them. And so order by is just what you see when you get the information back. So would you guys rather just cut over and look at the database that you have or talk through some examples on slides, which would be more helpful to you? An example? Okay. Okay, so let's say that we have a table called holiday schedule, and it lists the holiday status for let's say just UAMS. Okay, so for each holiday, it says whether UAMS is open or closed. So to find out whether we're having class or whether UAMS is open or closed during a holiday, we would select status. Status would be that column. So we would select status from the table holiday schedule where some business type equals school. So status in this case will be the name of a column in the table. Business type it is the column where the computer should look to find schools in there. So say we have a table and it's multiple business types in Little Rock. UAMS or schools is a school in Little Rock, so UAMS will be under schools. So we want to find out if UAMS is open, so we might select that status, open or closed, from the holiday schedule table where business type equals schools. So that's sort of how your select statements are going to sound when you write them. Does that make sense? Okay. There are operators you can use. So there are single row operators and multi-row operators, but let's just concentrate on the single row operators. So I might want to say I'm a primary care physician and I'm looking at my patients, and I want to know all my patients that that are not in good blood pressure control. So I'm going to select the patient number and the patient contact information, their name and their phone number from the vital signs table where systolic blood pressure is greater than 170. Makes sense? So I'm using that greater than operator in my where statement so that I can pull out only the rows, only the patient's data where their systolic blood pressure is greater than 170. Make sense?
Now you are putting one information on the row, not the row. Yes.
So, okay, so if you do a projection, you do a projection in your select statement, you choose only a certain number of columns. So if in my case, if all I want to know is their blood pressure and the patient name and their contact information and maybe the visit date, then I might select just those 4 columns out of that table. So I would say select patient number, patient contact, visit date, and systolic blood pressure, where systolic blood pressure is greater than 170. And that would pull me back all the patients and those 4 variables for them for the patients who had systolic blood pressure greater than 170. So maybe I can call them all up. I want a list so I can call them all up and see if they're checking their blood pressure regularly. So if we had, whoops, slide was grossly out of place. So I should have had this table further up in the slide deck. So this is an example of the holiday schedule table. Let's say it has 2 columns. It has a business type and it has a status in it for each of the holidays. Well, it has the business type, it has a holiday column that says which holiday, and then it has the status in it. So I would query that table, and there would in this table, if my 3 columns are business type, holiday, and holiday status, how many records would I have for each business type in here? Can you kind of describe it to me? If I added the column there that said which holiday, that indicates which holiday. So basically, if I want to know the holiday schedule for the businesses, I would have for each business, I would have a record for each holiday in there. Does that make sense? Yes? No?
Or you're saying you'd make a column for each holiday and then a
Right.
1-0 value, 1 being open, 0 closed.
Yeah, so the status column is that 1-0. And then there would need to be a column in here that says what the holiday is. Like if I want to know if it's open or closed on Christmas and Halloween and Columbus Day and President's Day and Labor Day. So there would be a column where the holiday name would be stored. There would be a column for the business type would be stored. And there might be, so say that this looks like maybe it's from the pick list, a business type looks like it's something from a municipality or a town. So in other words, in the town, all the government offices are open and closed on different holidays, maybe than the museums, maybe than the banks. And so there, for each business type, there'd be a set of holidays in there for which this status would be listed. So the number of records, there would be a number of records for each business type, depending on how many holidays they provide a status for. Does that make sense? Okay. So then if we query this table, and let's just say it's exactly as it is on this slide, where it's just 2 columns. So if we selected status from the holiday schedule table where business type equaled school, we would literally get this exact output. if it's as it was on the previous slide. So to retrieve a list of all open businesses, we might select the business type and the status, so both columns from the holiday schedule table where status equals open. So you got a projection of your two columns in the select statement, and then the restriction where status equals open is in the where statement. So if we ran that query on that old table back there, that's what we would get. And so if we expanded our example to have business name in there, we might have another table that had different businesses that stored what type of the business was. So then we have two tables. We have a business name table and we have a holiday schedule table, kind of like our patient sample and results that we talked about earlier. And so if we did that, then we could put in a business name and get the status, whether it's open or closed, rather than just all schools or all post offices or all whatever. So just some basic syntax stuff. SQL statements are not case sensitive. In the ANSI standard, I'm sure there's a system out there that does it a different way because it wants to, but all SQL statements end in a semicolon. If you don't have the semicolon, your statement won't run. You can use a star or an asterisk to show all of the items. So for example, if in our lab result, I wanted to look at everything, instead of saying I just wanted certain columns, I just select star from, and it would pull back all the columns in the table rather than doing a projection or limiting the number of columns that I returned. So say I have a table, it's a database called, say it's a database for the placebo study, and the table name is DMOG. So I might select star from placebo.demog, demog underbar update is the actual name of the table. And so select star from, meaning it just pulls back all the columns. There are also SQL functions. These functions in SQL are generally different than how you might do it in SAS. Those two carets back to back like that means not equals. So Sharab or Mahanez, can I get you to come plug up and do some examples in the database, run some example queries?
You want to post this, or you want the website to
No, just do it with what they have installed so that they can see what it would look like. Okay, so for those of you online, can you log into Blackboard? Okay, so those of you online are not going to be able to see it. If you have, I'll keep my computer open and ask questions as Sharab is going through it. Okay, so I'm going to just put the mic between us. There you go. Okay, so when you do your query, if you can tell them, you're going to have to like tell them exactly what you're typing, so that they can type at home and make sure they get on the thing. And I'll I'll watch this machine for questions. Oh, sure, yeah. Okay, so for those of you online, Sharab's getting his stuff ready to demo. Oh, hey, Sharab, I know how to do it. Do you have Chrome? You do have Chrome.
Yes.
Can you log out of Blackboard and I can log into Blackboard on your machine? That way we can record it for them and they can see it online? Okay, all right, so online people, hang on. This is going to take a few minutes. We're going to make it so that you can see. Yay. Okay, it looks like it's working. Can you guys hear me? We just got the mic, we think, to work. Can somebody make a ding? Awesome, thank heavens. Okay, I'm sorry it took so long, guys. All right, so I'm gonna turn on the recording